we work for the DRDO mostly. So our projects comes from the DRDO. Our main task is to characterize the explosive molecules. So if I give a sample to you, can you able to characterize which explosive molecule is it or not? For that, this is our terahertz system. This is the femtosecond laser, and here it comes the laser. Here you have two photoconductive antennas. One, similarly like I explained, photoconductor, one generates the terahertz and other detects. Here it comes, the radiation comes, hits the sample, and you will get the detection part. The purpose of this was to find the spectra of the explosive molecules. Each explosive molecule has a distinct spectra in a terahertz region. That we call it as a fingerprint spectra. Like a fingerprint, no other molecule will have the same spectra as the previous one. So how do we do it? How do we extract the spectra of a molecule in here? First, instead of sample, we place a gold-coated mirror. Because gold-coated mirror is a metal, there is no absorption of terahertz radiation. It completely reflects back whatever the radiation has come. So this is the reflection from the gold-coated mirror. Now we remove the gold-coated mirror and place the sample of our interest. Let's say my sample of interest is RDX, an explosive molecule. After that, we compare the two spectras. Because if each and every molecule has an absorption bands in the terahertz region, that molecule absorbs certain amount of radiation, and each frequency has a different absorption intensity. So you will see this is the spectra, absorption spectra we get. For the RDX, you can see there are distinctive peaks: 0.8, 1.6, 1.3, 1.5, and 2. From 0.1 to 3 terahertz, you got a distinctive peaks. These peaks separate one sample from the other, and those peaks are not random. There is a completely theory established why those peaks are occurring at those positions. Because each molecule has a different structure, and when they absorb the terahertz radiation, the molecule vibrates in a different way compared to the other peaks. So that's why you get a distinct peaks. Now, these are the other premium explosives which will be used to study, generally used in explosive making or improvised devices. RDX, TNT, PETN. As you can see, peaks of RDX is different from TNT and PETN. These are the premium explosives. Similarly, HMX and tetryne. These explosives are different. So we have a database. Now we have a database of spectroscopy. Now we want to apply the machine learning to see how our spectroscopy data is enough for the machine learning to do the classification. Because we have different type of data. Here we'll get when you perform the experiment, we'll get 4 type of data. One is absorption coefficient, refractive index, and literal terahertz pulse you get. Yeah. Phase. This is also a data. So we want to see whether if we give this data to a machine learning algorithm, can it predict what compound it is or what kind of explosive it is. So for that purpose we have currently choose, because this will take a long process, but here the spectral peaks are distinct. So we want to choose the absorption spectra as an input data and perform the machine learning algorithm models to see whether the classification is perfect or not. So we have performed the same absorption coefficient data on the same sample at different positions. You can see for each sample, for each position for the same sample, our peaks are coinciding, but there is a spread in the data. That thing is mainly because of the surface roughness, angle of incidence, all those things come into picture. When you come to the natural application of this in the technology in the field, when we do it is in a laboratory condition, everything is free of error. But when it goes to the field, you will get a lot of errors. That's why we don't want to clean any of the errors. You want to let it there and see how our machine learning models comes into picture. Yeah. So these are our data. We have collected, so for 5 samples, each sample is recorded 60 times, and frequency range from 0.1 to 3 terahertz. So we have 90 features from 0.1 to 3, 90 features and 300 rows. each sample is labeled RDX, RDX, PNT, HMX, that's all the things. First task is to perform principal component analysis. You have a huge data. You want to see how the principal component analysis identifies the data. Now, advantage of the principal component analysis is that it reduces the dimensionality. Means useful unnecessary data is avoided. All the 300, whatever I said, 90 spectral features are reduced to 50. So rest of the 40 unnecessary data points are avoided. And I can see all the data are clustering according to their pattern. RDX, HMX is clustering, PETN. So this algorithm is identifying the patterns or what are the features present in the data. Now the new data which is come from the principal component analysis is spread into 3 classical machine learning algorithms. One is support vector mechanism. Support vector mechanism basically has the idea of creating now let us assume you have only 2 data points to separate, A and B. A simple line of this separation would be easy to say. This data is separation from this. Now I have a choice of drawing a line in n number of it. I can place my hyperplane here, here, here in this direction. All the 360 degrees are possible. What support vector mechanism does is that it will give you the say which plane is best suitable for the separation of the data points. This thing comes from the calculation of this margins. What margin is means you assume a plane and you calculate the Euclidean distance from that point to the plane and you maximize the distance. Similarly, you calculate the margin for each point to the plane. Calculate like this. You will get a set of distances. From the distances, you take an average and you will get an idea of hyperplane. This hyperplane separates the data from A to B. Now, if you give a new data point, the new data point calculates its hyperplane distance and tells which side it should go. That's one. Next algorithm is K nearest neighbor. Similarly, it also calculates the Euclidean distance between the points from one point to the next data sets and gets a set of distances. From the distances, it will try to classify the new data point which assumes which distance it is making for the new data point, and based on that it calculates. Third is random forest. Now previously I have shown you a data set of 1 to 60, 300 data sets. I am giving in the previous data, this algorithm, the data set is taken as similar form. There is no randomization, there is no changing in upon. When it comes to random forest, it chooses data randomly. Let's say I have given a 30 samples as a data, input data. Now it changes the data from one form to other form and randomly and creates its own data sets. From the data set, it makes a decision trees. Decision trees are simple, but we are saying a condition, whether that condition is satisfied by this data set. Now in this algorithm, condition is met by what you call distances and the data set approach or the diversity in the data set. Now you have all the different training data sets from the single data set, and you generate different decision trees. From that you do the averaging of those things and you try to predict this. These are the 3 algorithms we have used. Now let's see what is the result of these algorithms. Before going to the result, these parameters are going to be defined. You have performed the machine learning model on the data and you got a result, but you need to express the result in some terms such as specificity, the probability of positive test and negative test. These are just what you call terms. Accuracy is the most important term. Now here, true negative, true positive. Suppose my model has performed some calculation, but it is whether it is true or predicted is whatever it is prediction is true or not. That is true. If it is true, true positive. true and negative, it is true negative. So that's based upon that we will calculate these parameters. The more these parameters good, your model is working. And accuracy, basic term, there is no need to explain that. Yeah. So once you perform, these are my confusion matrix. First confusion matrix for the PCA plus SVM. So PCA data is combined with the support vector mechanism, and my accuracy is around 80%, sensitivity is 100, specificity is 71. So these are two labels. So what it does means, it is taking 5 samples from the HMX and how much predicting it is. So 5 are correctly predicted. HMX is predicted as HMX, it is not predicted as EETN, RDX, TNT or LA. Now if you take C, this one, PETN, 12 samples out of the 12 given data, 12 are predicted correct, rest of there is an error. One sample is predicted as RDX, another is predicted as TNT. This cross, whatever the diagonal boundary you are getting, that is the actual predicted number, actual correct one. The rest of the things are wrong predictions. So this defines your model and your accuracy, your sensitivity and specificity. Next thing is PCA plus KNN matrix. Similarly, you can see now we talk in terms of accuracy only. Accuracy of this model is 80%. Accuracy of this model is 81.66%. Now we move to the last model. Yeah. Random forest. Random forest accuracy is 86.66%. If you compare the three models, I have a good accuracy at random forest, which is predicting of 86.66% for my data. Now, important takeaway is that this is not always true. You can change the hyperparameters and you can improve your accuracy. By what do you mean by my hyperparameters? Before giving a data to PCA, what I did was normalize the data. You have plenty of options of normalizing the data. With each option, your normalizing parameters will change and your PCA results will be changing, and subsequently your accuracy will also be changing. This is one model we have tried which suits best for us. According to you, you can perform n number of normalizations, PCA conversions, standardization, all these things can be performed. Now this is entirely up to the classical machine learning algorithms. Next step is we have performed one-dimensional convolution neural network to classify the same data. Generally, convolutional neural networks are used to classify the images, a 2D image. You have a two-dimensional object, you do the process and do that. But there is a one-dimensional CNN available also. Since we got a spectroscopy data, our data is one-dimensional. Now we have inputted the same one-dimensional data into the one-dimensional convolutional network, and we carried out the same steps which are take part in a convolution, what you call classic convolution neural network technique. We have an input layer followed by convolution layer, pooling layer, flat and fully connected layer, and output. All the steps are in the same way as a classic two-dimensional convolution network, but we have chosen only one dimension. Now let's see the results. This model predicts an accuracy of 98.9%, sensitivity 100%, specificity 100%. You can see all of those are predicting correctly. Only one is predicted wrong. So neural networks has an advantage over classical machine learning algorithms. That's why people are so much crazy about neural networks. And you have a validation curve. My training accuracy is going from 98%. Validation accuracy is going from, both are coinciding at nearly 98%. My loss curves from 0.1 to they have reached to 0.2, both for training and validation sets. Now, in this thing, we have chosen as a train and test data as the what you call 80-20%. 80% we have given for the training data. No, sorry, 70-30. 70% of the data is given for the training. 30% is for the validation. And our data is limited to 300 samples. 5 pure explosives, which we have repeated for 60 recordings. So we got a set of 300 readings. Now if you have more data, let us assume you take 100 readings for a particular sample. Now your accuracy may increase in the what you call classical machine learning algorithm. So you need not jump to neural networks. So this is one of the observations we have found. So this is this thing is limited up to the spectroscopy part. We are simultaneously doing the imaging of the materials also. We want to use this same knowledge to classify the images, just like CNN does in normal images. We generate terahertz images also. We want to apply this CNN algorithm to terahertz images and see whether the classification is performed correctly or not. So that's it. This is from our lab. Thank you. Any questions? Yes. Yeah. Yes.
As sir, you told about absorption
Sir, I
as this frequency is gets absorbed by water molecules. Then I have to work in a very controlled atmosphere.
Yes.
Then I think what are the research?
Yeah. So when I say about water molecules, see, just a minute. Now, you see, you are getting a spectral band from 0.1 to 3 terahertz. In this region, there are only certain bands, matlab 0.2 or 0.4, 0.6. Only certain bands are heavily absorbed in the water. There are certain other regions which are completely not absorbed, like 0.2 terahertz, 0.1 terahertz, 0.3 terahertz. Those regions are not absorbed by the water bands. These, especially these regions are used for the communication purposes. Just like I've said that terahertz communication. So they will be using only 0.1 terahertz source and generating, try to communicate over the device. Either 0.3 terahertz source and try to communicate over the device. So you have when you take an entire band, this entire band, certain regions are heavily absorbed and certain regions are not at all absorbed. When it comes to water, you have to identify which regions are getting absorbed and avoid those regions and conduct your experiment. Ideally speaking, if you want to use this in a communication, people are working this entire communication industry in the what you call Iceland area, because there is so much snow and the water absorption is low. So they want to test these devices over there and later bring it on to actual fields. That is one of the things which you can't avoid. Any other? Thank you.
Good evening everyone. I am Nusrat Fatima on behalf of Department of Computer Science and Information Technology, Maulana Azad National Urdu University. Thank Professor Anil Kumar Chaudhary sir, Professor School of Physics, University of Hyderabad, for sharing his knowledge about introduction to quantum computers, qubits, Shor algorithm and almost everything about quantum optics and physics. And I also thank Mr. P. Naveen Kumar, Research Scholar, University of Hyderabad, for sharing his knowledge as well as giving us an implementation example of terahertz pulse generation detection and its machine learning implementation of the algorithm of explosives classification. Thank you once again. I thank all the participants as well for having sitting patiently and listening to the complete session. Thank you once again. Thank you, sir, for giving your valuable time for us for this session. Thank you, one and all.
Thank you.
End of the program?
Yes, sir.
Thank you.
Thank you so much.